Okay, so today I will talk about the Kleinian groups. So this is the key theory in the hyperbolic three-manifold theory. So there is a really great to talk about this, and I want to keep this the geometry and topology workshop going on. So anyway, I will talk about the Kleinian groups and their properties and some the important results about the Kleinian group theory. And I will talk about how the people develop the Kleinian group theory to the higher rank. So there is the key, the very important idea in the higher type space. So keep in mind important properties in the Kleinian groups for generalizing to higher rank. Okay, so the Kleinian group is a discrete subgroup of the isometric group of a hyperbolic space. So as you know, the discrete group is so some object induced from the GX the manifold GX the geometric structure. So the studying the discrete group is actually to study the GX the manifold. So that is why we study the discrete groups of the hyperbolic in hyperbolic space. Okay, so here there are two main references. So first is the Kapwich, the book, the hyperbolic manifolds and the discrete groups. And the second reference is the Connery, the Anderson representation, the informal lecture notes. So you can find this lecture note online. Okay, so first, so let me get started with the basic properties of hyperbolic spaces. Okay, so here the basic the models of hyperbolic space. So actually there are many the models of hyperbolic space. So but here I will give some the projective model of hyperbolic space. So let the Rn1 be the real vector space and n plus one dimensional real vector space with the symmetric bilinear form of the signature n1. So signature n1, the symmetric bilinear form can be written by like this matrix form. So J. So J is a diagonal matrix with all entry one except the rest the entry is -1. So if you have a signature n1 the symmetric bilinear form, then there is some vector with a negative norm and some vectors with a general norm, and there is the norm vectors with a positive norm. So just take all the vectors with a negative norm first. We define the V minus, and the set of the space of all the vectors with zero norm by the V0. So then by using the standard projection onto real projective space, the RPN, then you can define the hyperbolic space as a projectivization of V minus. And its boundary is defined as the projectivization of the V0. Okay. So then on the fine chart, xn plus 1 equal to 1, then you can see easily the hyperbolic space is actually the unit ball, this one. And the boundary of the hyperbolic space is n-1 sphere. Okay, so then here, okay, so hyperbolic space is defined as the space of negative the vectors. So then you can see that the symmetric, the binary form of signature N1, so gives rise to the positive definite symmetric bilinear form on symmetrics on hyperbolic space. So that gives us a Riemannian metric on hyperbolic space. So you can write down explicitly the metric, Riemannian metric. So like this. So then you can compute its sectional curvature. Then it turns out that the sectional curvature is -1. And so this picture is some show you the many kinds of models of hyperbolic space. So this is in three-dimensional case. So you have I mean the R21 case. So this cone, this cone is null cone. So that is the correspond to pre-zero. And then the inside of the cone, the correspond to the space of all the negative vectors. So first, you can see that the by projectivization, I mean, by using, you can add on the affine chart x3 equal -1, equal 1, you can see the Kleinian model like this. So, and if you normalize the negative vector, it's no -1 as -1, then you can see the hyperboloid the model like this, the blue one. And by using the -1, so this point is a 0, so 0, 0, -1. So you can connect the hyperbolic any point, the hyperbolic point, and this point. So this line gives us some point in xy plane here. Then the correspondence gives the Born model. And the Bunker model, the Born model. So you can project the Bunker any point on the Bunker model to the upper hemisphere. So this one, sorry. So this one. So then, and by using the stereographic projection to this point, then you can find the alpha space model. So anyway, there are many the models for the hyperbolic space. So we will use one of them for the purpose. Okay, so now I will give you a definition of the graph for hyperbolic space. So this is the generalized the notion of hyperbolic space, so suggested by the Grunwald. So Grunwald want to collect the key property of hyperbolic space. So and then he want to generalize this space to some metric space. And here, all the property of group hyperbolic space. So space is the key properties of the hyperbolic space either. So I will give some important properties and the results about the group hyperbolic space. Okay, so group defined proper the rank space X is a graph delta, the hyperbolic. So whenever T is a geodesic triangle in X with a three side, the S1, S2, S3, and pick up any point, the Y in S3, then Y is contained in the delta neighborhood of S1 union S2. So that is a definition of that hyperbolic space. So here is a picture. So this gives us what idea is in the definition of the group hyperbolic space. So in spherical geometry, if you draw the triangle, then you have some, say, the thick the triangle, and in Euclidean space, so you have a flat triangle. In hyperbolic space, actually, so you have a thin triangle, so like this. So this is so just a key property of the growth hyperbolic space. So keep in mind that the picture when we study the growth hyperbolic space. So then you can easily prove that hyperbolic n space is a delta hyperbolic. So you can find the delta explicitly. So delta is a tangent hyperbolic inverse of 1 over the square root 3. So there is that means that the hyperbolic space is also the growth hyperbolic space. Okay, so then I will define some notion. So some quasi thing. So first, define let x, y complete the metric space. Then a map f x from x to y is called the KC, quasi isometric embedding. Means that for any x prime, the x point, then so this inequality is satisfied. So if you can notice that k, if k is 1 and c equals 0, then actually so f is isometric. So this means that you just already deform the isometry, then you can obtain the quasi-isometry, the things. So there is the notion of the quasi, the isometric thing. Okay. So then we will say that the quasi-isometric embedding from the interval into X, the KC quasi-geodesic in X. Okay. And so moreover, so F is a quasi-isometric embedding and coarsely surjective. So coarsely surjective means that so the image is actually C dense in Y. So it satisfies this one. Then we say that the F is a quasi-isometric. So that the quasi-isometric embedding, quasi-isometric, the quasi-geodesic, quasi-isometry is a very important thing in the group hyperbolic space. So here is gives some picture. So this, okay, so this kind of thing is the quasi-geodesic. So this is geodesic. So red line is geodesic. So if you perturb the geodesic a little, then you can have the quasi-geodesic. Okay, and one more thing we need. So XY, the metric spaces, then if you have the homomorphism from the X to Y, then the mapping F is called the quasi-conformal. So this term is bounded away from the index. So if you look at the definition, so actually, so at the HF is so measure the how F deformed the unit bore into in Y. So ellipse. So here, so it's circle. F maps to the some. Ellipse. So then, So f is one, so hfx is 1, then the circle is f maps the circle to the circle. But anyway, the f we want to measure so how the deform the f how f deform the circle into how the thin the ellipse right there. And also so so causiform map is measures how the angles is deformed and like that. Okay, so this theorem is a very important theorem in group hyperbolic space. So so-called the Faro-Trevor property. So let X be a delta hyperbolic space, and the F is the K quasi-isometric embedding. So KC quasi-isometric embedding. So that means that F is a quasi-isometric, quasi-geodesic in X. So there is a constant R, so only depending on KC or delta. Then so the Hausdorff distance, so between the image of F and the geodesic, the connecting the endpoints of the F is bounded by the uniform constant R, like this. Okay. So that here, this in the Faro-Trevor property, the R is important that the R is only depends on the KC delta, not R is independent of the choice of the KC quasi-isometric embedding. So that is a key thing in the Faro-Trevor property. So by using the Faro-Trevor property, you can prove that suppose the x, y, and proper the rank spaces, and there is a quasi-isometric embedding the f from x into y. Then so y is a hyperbolic, then x is also hyperbolic. So that means that so the only so group of hyperbolic space can be embedded into a group of hyperbolic space. Okay. So this picture, so also to show you what is the meaning of the Faro-Trevor property. So if you have a quasi-geodesic like this, and you join the 2 points by a geodesic, then the RKC quasi-geodesic is contained in the neighborhood of the geodesic joining the 2 endpoints. Okay, so we will use this corollary later. Okay, now we define the growth boundary of a delta hyperbolic space. So for a delta hyperbolic space X, then let the Gx is the collection of all the geodesic ray. Actually, the alpha is the isometric embedding of the half infinity interval into the X. So this is a kind of geodesic ray. So, and we give a relation on the Gx. So like this. So two isometric embedding alpha and beta are equivalent if the distance is bounded. So then this relation becomes an equivalence relation. Then we can define the space of the equivalence classes. So we call the space of all equivalence classes the group boundary of delta hyperbolic space X, like this. And also we denote by the alpha infinity, the class of the equivalence class of alpha in the group boundary. And there is an important fact here in hyperbolic space. So every point in X is joined to every point in the group boundary by a geodesic ray. So that means that if you define the space of all the geodesic ray, starting at the fixed point x naught, then that also gives us a group boundary like this. So this is actually the definition of ideal boundary. So you can see that given some Riemannian manifold, you can define an ideal boundary. It's an ideal boundary, or like this. Think of all the geodesic rays, and gives the equivalence relation like this. So then you can define the ideal boundary of Riemannian space. So, and then we topologize the X union and the boundary infinite boundary of X, group boundary of X, like this. So alpha n, so here, so alpha n is a sequence of the group boundary. So this sequence converts to alpha, means that if, so there is a point, the base point, x naught, and there is a beta n, so this is a geodesic ray starting at x naught. So, and also the beta n, they represent the equivalence class of the alpha n. So then the beta n converts to the beta, the geodesic ray, so representing the equivalence class of alpha. Okay. So this gives some topology on the group boundary. And also the xn is a sequence in space X. So xn converts to alpha if, so there is a base point x naught, and so geodesic beta n, starting at x naught. And then the beta n, Rn is equal to xn. So that means the beta n pass through the xn, such that the beta n converts to the beta, so which represent the equivalence class of alpha. So here you can draw the picture. So x naught here, so x1, x2, something like that, xn. So you can draw the geodesic. So geodesic converts to is beta. So beta is so representing the equivalence class of alpha. Okay, like this. So this gives the topology on the X union, the group boundary of X. Okay, so there are many the results on this topology. The first, so the xn converts to the g. So xn is a sequence in X, and g is a point in the group boundary. Then if other sequence yn is bounded by so xn yn is the distance between xn and yn is bounded by the r, or constant r. So then the yn also converts to h. And second, so the group boundary, so compactify the space X. So that means that X union of and the boundary of group boundary of X is compact. So, and third, if you choose two distinct points on the group boundary, so then always there exists a geodesy joining so G and W. Okay. So that means that the alpha minus the infinite is Z, and alpha plus infinite is W. So that is the some important property of that hyperbolic space. So usually this. So for example, the Euclidean space does not satisfy this one. Okay, so I will explain the why. So this is the important property in that hyperbolic space. Okay, so next, so any joining any two geodesic joining the two distinct points G and W given the two distinct points, right a house of distance and most two delta apart. So that means that if you choose the two distinct points on your group boundary, and we know that there exists geodesic bi-infinite geodesic, so joining them, but maybe the geodesic maybe not the unique. So even though there is another geodesic joining them, the house of distance is uniformly bounded by the two delta. Okay. So in hyperbolic space, so in Hn, actually there is a unique geodesic joining two ideal points. Okay. And from this the lemma, you can prove this proposition. So xy that hyperbolic space and f at the Cauchy-symmetric embedding from the x into y. So then there is a continuous injective map. So on the level of Gromov boundary. Okay, so a map from the Gromov boundary of x into the Gromov boundary of y, like this. And also this is continuous. Furthermore, f is a Cauchy symmetry, then this map is a homeomorphism. Okay. So actually, this map can be obtained by the Faro-Treiber the property. So if you have a geodesic here, so x here is geodesic, so f gives if f is a Cauchy symmetric embedding, then f maps geodesic into the Cauchy geodesic. So then the Cauchy geodesic in hyperbolic space so gives us some 1 point on the Gromov boundary exactly. So by using this fact, you can define the boundary map on the level of the Gromov boundary. Okay, so and here I want to explain the difference between hyperbolic space and Hadamard manifolds. So because as you know, the Hitchin representation acts on the symmetric space of higher rank. So it has some so total geodesic, the isometric to the Euclidean space. So, and also it has a non-positive sectional curvature. So there are many differences between the negative sectional curvature geometry and non-positive sectional curvature geometry. So I want to give you how they are different. So first, what is a Hadamard manifold? Hadamard manifold is a complete, simply connected Riemannian manifold with everywhere non-positive sectional curvature. Okay, so actually the hyperbolic space is also the Hadamard manifolds. So Hadamard manifolds allow the sectional curvature can be zero. Okay, So usually the symmetric space of non-compact type is Hadamard manifolds. So, okay. And then we can define the visual boundary of Hadamard manifolds, right? In the same way as the delta hyperbolic space case. So just the set of, think of the set of all geodesic rays and gives a relation between on the space. So by using this, by using the Hausdorff distance between the geodesic rays, then the boundary is defined by the set of the all equivalence classes. And also this, there is the cone topology on the boundary is defined by like this. So this is also similar to the topology on the group boundary. Okay. So then any Hadamard manifolds is actually the homeomorphic to Rn, and also each boundary can be identified with a unit tangent bundle at some point. Okay, so this is a homeomorphic to the n-1 sphere. So topology is very simple. So, but okay, so but they have a so different geometry against the hyperbolic space. So, for example, the y, if you take a y is the symmetric space, so associated to the SL3R. So, if you quotient the SL3R by the SO3, then you can have some space. So this is a symmetric space. So 5-dimensional symmetric space, and also it has the symmetric Riemannian metric, whose sectional curvature is non-positive. Okay, so and also the Y is the Hadamard manifolds, and also the in Y, so two-dimensional Euclidean space is embedded in Y. Okay, so E2 is contained in Y. So actually, so E2 is a torus geodesic subspace of Y. So then the FTF, so this is the Fallot-Treiber, the property fails in the Hadamard manifolds. So because here is the example. So in Euclidean space, you can define some spiral, some curve by this equation. So then you can prove that this curve is a quasi-geodesic in two-dimensional Euclidean space, but it does not satisfy the Fallot-Treiber property. So if you connect to like this, like this, then you can easily see that the Fallot-Treiber property fails in this case. Okay, so Fallot-Treiber property is the property in the delta hyperbolic space, not Hadamard manifolds. And also, if you have two distinct points in the visual boundary of Hadamard manifolds here, so in delta hyperbolic space, if you have two distinct points, then there is the geodesic, the bi-infinite geodesic ray, geodesic joining them. But here, the situation already quite different. So this is E2. Then the visual boundary of E2 is a circle. You can easily see that. So then if G and W are opposite means that so G is minus W, then there is a geodesic joining them. So like this. So like this. Okay. But so it is not unique. So there are infinitely many geodesics joining them. So here, so So this geodesic, so this vertical geodesic, so connecting so this point and this point, 2 points. But these all the geodesics so are equivalent. So that means that that gives so the same that has the same endpoints on the visual boundary of the E2. So there are many the geodesics and there each of them and also they are not bounded by the constant some constant r. So that means that if you choose a geodesic, then any r neighborhood, so r neighborhood. So there is another some geodesic ray the outside the R labeled, any R labeled. So this is a different property in the Hadamard manifolds. And also if G and W are not opposite, so like this, then there is no geodesic joining them. So in Hadamard manifolds case, some different thing happens, unlike the hypertext hyperbolic space. Okay, so here, I want to explain some difference between the hypertext hyperbolic space and the Hadamard manifolds. Okay, so next I will describe the isometry of group hyperbolic space. This also works in the hyperbolic space. So on isometry, G is called elliptic, the parabolic, or pseudomic. So elliptic means that if the orbit, so G and X, is bounded, so then we say that the isometry is elliptic. And if it is not elliptic and it has a unique fixed point in the boundary of X, group boundary of X, then we say that on isometry G is a parabolic. And lastly, it has exactly the two fixed points in the group boundary of X, and one of which is attracting and the other of which is repelling. So then we say that isometry G is Rossudwick. So then there is a theorem. So this is a kind of classification of isometry of group hyperbolic space. So let X be a group hyperbolic space, then any isometry of group hyperbolic space is either elliptic, parabolic, or Rossudwick. Okay. So this is also the works for the hyperbolic space because hyperbolic space is a group hyperbolic space. Okay. Okay, let's see in the hyperbolic space case more detailedly. So the hyperbolic space, the isometric group of hyperbolic space is a orientation preserving isometry is a PON1. So A is preserved the J matrix. So then for each the isometry G, you can define a number, so-called the translation length, like this. So it measures X, Gx, so this distance over all the X in hyperbolic space. So there are then three types of isometry: the logarithmic, the parabolic, elliptic. So then you can easily see that the elliptic means that G fixes a point in X, Hn, and the parabolic means that the translation is 0. So Rossudwick means that the translation length is a positive. Okay. So I want to explain the dynamics of each isometries. So first, the logarithmic element, it has a two fixed point here on the boundary, and also, so this H plus is attracting fixed point. This H minus is a repelling fixed point. So dynamics, it looks like this. Okay, so every point is going to the H plus by the H action, and it has a invariant geodesic, joining the attracting fixed point and the repelling fixed point, and the H acts on this geodesic, the invariant geodesic, by just a translation. And actually, the translation length is so this translation length. Okay, so this is the dynamics of the logarithmic element. And this here, the second is the parabolic isometry. So parabolic isometry has a unique fixed point on the boundary, so H plus. So then this is a kind of the ball based on the H plus, so-called the hollow ball. So the H, leave each hollow ball based at the H plus, the invariant, and also so H acts on each hollow ball, like the translation, okay, like this. The lastly, the elliptic element is actually the rotation. Okay, so like this. So it has a unique fixed, no, not unique. Anyway, the fixed point inside the hyperbolic space, and it rotates around the fixed point of the elliptic isometry. So, okay, so here gives some dynamics of the elliptic isometry. So n equal 2 case, you can classify all isometry in terms of the trace. So if you think of the upper half space model in the complex plane like this, so the hyperbolic two-dimensional hyperbolic space is identified with the space of all the complex number with the positive, the imaginary part. So then the isometric orientation preserving isometric group of H2 is the Möbius transformation, as you know. So so this is the PSL2R is the orientation preserving the isometric group of H2. So then there are the equivalence condition for each isometry. So A is the isometry, the logarithmic, if and only if it's a trace is bigger than the 2. I mean, the absolute value of the trace is bigger than 2. And the parabolic case, so trace is plus minus 2, and the elliptic case, so trace is between the minus 2 and the 2. Okay, and also the A, if the logarithmic element A is the conjugate to the diagonal matrix like this, and the parabolic is like this, and the elliptic, the isometry is conjugate to the rotation, the matrix. Okay, and n equal 3 case, and also you can think of the off-hyper space model by using some quaternion number, so J. So this J is a quaternion number. Then the action of PSL2C action like this, so like the Möbius transformation in the hyperbolic two-plane case, then the orientation preserving isometry group is PSL2C. Okay, so in this case, you can also classify all the isometry in terms of the trace. Okay, Okay, so then, so given the subgroup of the hyperbolic space, so now that we think of the invariant, the gamma invariant of the set in the boundary of the Hn. So because if you have a discrete group in the isometric group of hyperbolic space, so this group acts on the hyperbolic space and also on the group, the boundary of the hyperbolic space. Okay, so there are two actions of the discrete group. So there is a the important thing you have to keep in mind. So because it turns out that most the information on the gamma action inside the hyperbolic space is encoded in the boundary action. Okay, so if you want to study the gamma action on the hyperbolic space, then by looking at some gamma action on its boundary, you can see that how the action is inside the hyperbolic space. So that is the idea of the limit set, the behind. So anyway, the gamma is given the subgroup of the isometric of hyperbolic space, then you can define the limit set. So the limit set is actually the intersection of the boundary of the Hn and the orbit of the gamma. So if you take a closure of the gamma orbit, then you have the space of accumulation points on the boundary of the hyperbolic space. So that is the limit set of gamma. Okay, and so this limit set is defined independent of x. So this is from the delta hyperbolicity of hyperbolic space. And also the subgroup gamma is called the elementary if the limit set is less than 2 points. Otherwise, gamma is called the non-elementary. So then F is the gamma is a non-elementary, then its limit set is perfect. So actually the infinite. So that means that if non-elementary the discrete group, gamma has lots of the limit points. And also the set of the fixed points of the Roxodrome elements of gamma is dense in the limit set. It's a limit set, okay? If gamma is non-elementary. And the limit set of gamma is the smallest gamma invariant across the subset of the boundary of a hyperbolic space. And the complement of limit set in the boundary of a hyperbolic space. So we say omega gamma. So this is the domain of discontinuity for the gamma action on the boundary of a hyperbolic space. Okay, so that means that if you have if gamma action on the hyperbolic space is the property discontinuously, so then gamma also has the property some domain in the boundary of hyperbolic space on which gamma acts the property discontinuously. So gamma has two domains, so on which the acts the property discontinuously. So we analyze two actions. Okay, so I finished give a definition of the Kerr graph. the first door. I want to finish the first door. Okay, so let gamma be a finite generated group with a symmetric generating set. Then we can define a graph, so-called the Kerry graph. So its vertices is just a gamma, and the edges. So that means that. So write this. So H is a GS for some generator S. Then we set this pair as a set in the Kerry graph. Okay, and assigning each edges that has the unit rank, then this Kerry graph turns into a metric space. So for example, the rank to free group. So we choose a standard the symmetric generating set, then you can draw its Kerry graph. So here is E, and there are the 4 edges, A, B, B inverse, A inverse. Here again, so AB, AA, AB inverse, like this. So this is a Kerry graph of a rank 2 free group. Okay, so and also we call the gamma the hyperbolic group. So if its Kerry graph is a group hyperbolic, so group hyperbolic, the notion works for the metric space. So we have the Kerry graph associated to the finite generated group gamma. Then we can check that the Kerry graph is the delta hyperbolic or not. So if the Kerry graph is a delta hyperbolic, then we call the group a hyperbolic group. Okay. So for example, any free group is a hyperbolic. Actually, it's a delta. So delta is zero hyperbolic, because so this is tree, right? The Kerry graph of a rank 2 free group is a tree. So there is the unique geodesy, the joining the 2 points, and you can check that the triangle is a zero thing. So any free group is the group hyperbolic. And also the surface group with a the closed surface group with a negative Fourier number is the hyperbolic also. Okay, and so in Kerry graph, we need the symmetric generating set, right? So, but if you change the symmetric generating set, so the Kerry graph is changing, right? But the Kerry graph is isometric to each other. Okay. So C gamma S and C gamma S prime is a quasi-isometric. So because of that, it's a boundary. If you have the hyperbolic group, so that means that if you have the Kerry graph is a hyperbolic, so then it's a hyperbolic. You can define the group boundary of the hyperbolic space, the Kerry graph C comma S. So then the group boundary is homeomorphic to the C comma S prime. So that means that its group boundary is independent of the choice of the symmetric generating set. Okay, so we write in this case we define the boundary of the gamma like this by the group boundary of the Kerry graph. Okay, and we call it the group boundary of the hyperbolic group, the gamma. Okay. Okay, so next talk we keep talking about the Kleinian group.